The term real numbers before? What is a real number? Does anyone have like a definition for what a real number is?
Is that any number above 0?
Any number above 0? Well, negative numbers are real numbers too. Okay?
A number that's so big that you can't even like deal with it.
Real numbers can be small. Basically, I mean, it's kind of a loaded question because you guys have been dealing with real numbers your entire math careers.
Is it like a number without decimals?
Decimals can be numbers as well.
It's just a letter.
Today we're going to venture into the realm of imaginary numbers. Okay? Have you heard of those before? Imaginary numbers.
Yeah.
You've probably heard of them. You probably haven't dealt with them that much. Okay? So here's a little comic on the screen. We've got pi saying to I, get real, and I saying to pi, be rational. Okay? Okay, the reason it's funny is because pi is an irrational number. It's a number that repeats itself, but never. It's a number that goes on forever and ever, but never repeats itself. Okay? I is an imaginary number, so pi is telling I to get real, and I is telling pi to get rational. You had to be there, okay? All right, so let's go straight to the slides. You did your reading, and I'm going to have some helpers help you with something today. So if you are ready, great. I will get to you in a couple minutes. Okay. Okay, so here's the thing. If I were to ask you to solve this equation, okay, if I were to ask you to solve f of x equals x squared plus 1 and find zeros, you might do something like this. Okay, well, zeros means I need to set this whole thing equal to 0 to find where its x-intercepts are. So if I do that, 0 equals x squared plus 1, how am I going to get x by itself?
Can you subtract the 1 over and then square root it?
Yeah, let's subtract the 1 over. So we have negative 1 is equal to x squared. Square root cancels the root out. We've got x is equal to the root of negative 1. Does anybody see something wrong with this picture?
You forgot the plus and minus?
Yeah,
Okay, true. But do you see anything else wrong with this picture?
the negative.
You can have a negative. Square root is negative.
We cannot square root a negative number. Nothing times itself will give you a negative number. Okay? Does that make sense? You should be familiar with that. Nothing times itself can give you a negative number. So here, we call this the imaginary unit. Okay, I want you to write that down. Root of negative 1 is the imaginary unit. Okay? Now, we use a symbol to represent the imaginary unit. We use the symbol I. Okay? I, that's not a J, that's an I. I is equal to the root of negative 1. So that's kind of your most important thing I want you to know today. You can't do this, so it's an imaginary unit, and we're going to make it I. Okay? Cool. Now, let's talk about what this would look like on a graph. Because we're always talking about how zeros are the x-intercepts of a function. If we cannot find zeros of a quadratic function, what does that tell us about what the graph of this quadratic function looks like? It doesn't have any zeros.
It's not touching the x-axis.
It doesn't touch the x-axis at all. Okay? So, for example, this right here, it's the parent function shifted up 1 unit. So it's a parabola that looks like this. It never, ever, ever touches the x-axis. That's why we cannot do this. Okay?
That's why it has.
Okay, no x-intercepts because we cannot square root a negative
So
number.
is that square root of negative 1 on a graph?
Say again?
Is that the imaginary number on a graph?
Yeah, that's an imaginary number. Now, it's kind of hard to comprehend imaginary numbers because they're imaginary, right? But just think of it this way. The x-intercepts are non-real. They're imaginary numbers. Okay? If you're having trouble with this, just process it and keep going with me.
All of them or just the square root negative?
Anytime you square root a negative, whether it's positive or negative, anytime you're squaring a negative at all, it's got imaginary roots.
So it's just the square root negative.
Just square root a negative. Okay?
What was the positive?
If it's a positive, you can square root a positive and get a positive and a negative solution out, but you can never ever square root a negative.
Yeah.
Good. Cool. So let me show you a couple examples of this in action. I'm gonna get a darker marker for my friend Isabel over there. Let's do purple. So for example, let's say that I give you the square root of -4. Okay? We know that we can never square root a negative number, but 4 is a number that we can square root, right? So if we thought of this as another way of saying the
-2.
square root of -1 times 4,
Oh.
I can then bring out 4's root and leave my imaginary unit inside. Okay, so let's bring out the square root of 4, which is what? Okay, so I'm going to bring that 2 out. I'm going to leave my imaginary unit inside. And because I defined my imaginary unit as I can substitute I in. This is the square root of -4.
I have a question, Mr. Barris.
What's your question?
Why did you change -1 times 4 and you changed it to 2? I'm just kind of confused.
So whenever you're given a negative root,
Yeah.
you still want to try and evaluate what the root is. Like, even though we can't take a root of a negative number, we can take the root of 4. Okay, so what I'm going to do, instead of writing the square root of -4,
You changed it.
I'm going to change it so that my 4 is positive, just being times by a -1,
Okay.
and then I can bring out 4's roots and leave my imaginary unit there.
Oh, that makes sense.
Okay? Feel good about that?
Yeah.
Cool. Let's go to our first helper for today. Who is our helper?
Here, check the list.
No, okay.
Our helper for today is Isabel Magana. All right, Isabel. I'm gonna put you over here. Okay. Do you have a problem prepared for us?
Yes.
Let's go ahead and show us how it works.
Thank you. Okay. So my problem is basically 3 in the square root of -16, and you have to factor out -1, so you go 16 times -1.
Cool.
And then you have to find the product property. Basically, you will do 3 times 4.
And where did she get that 4 from?
The 16.
Yeah, square root of 16 is 4. Good.
And then you have to simplify. So then 12 -1, and then your answer is 12.
Good. Let's give Isabel a hand. That was flawless. Good job. Okay. Pretty much the exact same thing we did over here. She took her negative root, she broke it up into the product of a actual square rootable number and the imaginary unit. She brought out 16's root and multiplied it by the constant that was already outside. And then she substituted her imaginary unit I in for the root of 1.
3 times 4 is 12.
Say again?
Wait,
No, no.
how?
Yeah, 3 times 4 is 12, so that's just a simplification step there.
Oh.
Okay? Cool. Nicely done. Let's keep going. Any questions on that? Okay. Easy enough. Okay, there's lots of examples for you to try out on your own. Let's try something displayed a little bit differently. Let's say you're actually solving an equation instead of just evaluating something. So here we were just evaluating some negative roots. Let's go ahead and bring an example where we solve roots. And I think Anaya will be my helper for this one, right? Can I erase? Yeah?
You can raise.
Okay, so next topic in your notes. I put solving equations with imaginary numbers. Okay? So for example, I could give you something that looks like this. X squared is equal to negative 144. Okay? Now right off the bat, you should be able to point out how I'm going to get x by itself.
Square root.
Yeah, square root, right? That should be like a natural response. Whenever you see x squared, to get it by itself, you have to square root. So if I square root both sides, x is equal to the positive or negative root of negative 144. Okay? Cool. Now Anaya.
Yeah.
That's just exactly what Isabel did. Once we get to this point, how do I evaluate a negative square root?
Well, I mean, wouldn't you just kind of pretend it's not negative for the most
Okay.
part, and then just keep it like just go as you would square root it as a positive
As if it were
number.
positive. Good, I like it. So, if we treat this as if it were a positive 144 just being times by a negative, how would I evaluate that now?
You would find the common factors or
The square root. What times itself?
12.
There you go. Good. I'm going to bring out the positive root. Okay? And now I've got root of negative 1. Okay, now my imaginary unit. Which letter did we use to represent the imaginary unit? I. So I could just rewrite this as positive and negative 12i. Okay. Now the ones me and Isabel did before, I forgot that these positive and negative need to be there. So just remember that. Anytime you're taking a root, regardless of whether it's a real root or an imaginary root, you gotta have the positive and negative there. Okay. I didn't call you up here because you're kind of in the back there, so I just thought I'd like have you walk me through it.
Okay.
Okay, let's give Anaya a hand. Good. Okay, now it's going to get a little trickier than this. Sometimes they'll throw equations at you where you've got your constant term and your ax squared term on the same side of the equal sign. Okay, you would just need to move that 90 over and get x by itself by division and then rooting. Let's look at something even trickier though, because this whole unit so far we've been talking a lot about factoring, completing the square. Let's bring some of that into the class. Okay, so let's do. Oh, before we do that, so hold on. I got another vocabulary word for you. We just talked about what imaginary numbers are. Imaginary number is whenever you're rooting a negative number. Here's another definition for you: a complex number. Okay. So in your notes, go ahead and write down the words complex number, complex numbers. A complex number is any number written in the form a plus bi, okay? Where a and b are real numbers and I is our imaginary unit. Okay, so A and B are real numbers, and we already know that I is my imaginary unit, which is just equal to the square root of negative 1. Okay? Every complex number has two reals, but the second real is being multiplied by the imaginary unit. Cool. You feel good about this?
What was the definition for imaginary numbers?
Imaginary number, and I apologize for not writing that down. Let's do that right now. An imaginary number is any number obtained by rooting a negative number. Okay? Any number obtained by rooting a negative number. Okay?
Okay.
So a complex number has an imaginary number inside of it, but it's also got some reals in there as well. Okay? Here's your next bullet point. Two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. Imaginary parts are equal. Let's show you what I mean by that. And we're almost ready for our third helper of the day, who is Colton. Colton. Yeah. All right. Let me give you an example first, and then you're going to walk me through the next one. Okay. Okay, so we're getting this definition down. I'm going to do an example for this over here, so it's a little bit higher, but make sure you get this in your notes. Okay. So example. Let's say that I give you an equation that looks like what's on the screen. 4x plus 10I is equal to 2 minus 4y times I. Okay? That's really small. Let me rewrite that. I got more room over here. So 4x plus 10I is equal to 2 minus 4y times I. And I might give you the instructions. Find x and y that make the equation true. Okay? Those are instructions for a problem of this type. This concept told us that two complex numbers, and remember, complex numbers, anything that can be written in this form. So you'll see over here, this right here is a complex number because we've got something real and we've got an imaginary unit. Here is another complex number. We've got something real and we've got an imaginary unit. Okay, so these are both complex numbers. This is a complex number and this is a complex number. Now, we said in this bullet point that two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. So here's the real part of this number. Here's the real part of that number. So these are real. So for these two complex numbers to be equal, their real parts must be equal to each other. Okay, so I'm going to take those real parts and set them equal to each other. Now, what value of x would make these real numbers equal to each other? How would I get x by itself?
Divide by 4.
Divide by 4, okay? That's gone. X is equal to 2 fourths, which can be reduced down to what?
4/2.
A half, okay? So once again, we took our reals, we set them equal to each other, we got what x has to equal, okay? We're going to do the same thing here with our non-reals. If we take our non-reals, I'm going to switch colors. If we take our non-reals and set them equal to each other, we need to figure out what value of y would make that true. So here's my non-reals. These are non-reals. We're going to set them equal. So 10I is equal to 4yi. Okay, now how am I going to get y by itself? It's being times by 4 and I.
Divide it.
Divide it, right? Opposite of timesing is dividing. So what do you think I should divide first?
Divide out 4.
Let's divide the 4 out. Okay? So those are gone. Now I've got 10 fourths. I is equal to yi. Right?
Divide out y, right? So they can't see.
Well, we want to divide. We want to get y by itself. Did you say y or I?
I.
Sorry about that. You divide the I out. So those are now gone. And we've got I divided by I on the other side, so those are gone. So y is equal to 10 fourths, which reduces down to be what?
5/2.
5 halves, good. Okay? So we've got our values for x and y, which make this statement true. So the main thing you got to remember, anytime you're equating two complex numbers, you take their reals and equate them. You take your non-reals and equate them. Does that make sense?
Yeah.
Yeah? Okay. Sweet. We can check our answers really quickly. Here we did get x equals 1/2. Oops. And we got y is equal to, oh, did I forget a negative somewhere? Solution says -5/2. Did I forget a negative?
Is a
Oh, there was a negative there.
-4.
Forgot about that. There's a negative there, which will make all of this negative. Okay. Cool. All right, Colton.
Oh.
You ready?
Good luck, Colton.
You're gonna get a problem that looks pretty much exactly the same format.
Okay.
Main thing is take your reals,
Yeah.
equate them. Take your non-reals and equate them. You want to come up? Do you want to sit where you're at? You sit where you're at? Okay. Being too easy on you guys. Okay, so here's an equation. I'm going to erase the words. I'm going to keep this up in case anyone needs it. Okay? Let's get this stuff out of the way. So example again, we've got 2x minus 6i is equal to -8 plus 20yi. Okay? Let's go ahead and talk about what is real in this equation.
2x and -8.
Okay, so these are my reals.
Oh my god.
And what's my imaginary?
-6i and 20y.
Okay, so I'm going to call them imaginary or non-reals. Non-real. Non-real. Okay, so how do I figure out what x and y have to be to make this statement true?
Wouldn't you do 2x equals -8?
Yeah, you take your reals, you equate them. Okay, let's go ahead and get x by itself.
Divided by 2.
Divide by 2. So x is equal to -8 divided by 2, which is -4. Good. Okay, I got my x down, that's done. How am I going to get my y?
You have to do -6i equals 20y.
-6i is equal to 20y I. How am I going to get y by itself?
Divide by 20.
Divide the 20.
Sorry.
Okay. So those are gone. -6i over 20. Let's go ahead and reduce that really quickly. What is 6/20 reduced down to be? Good. Nicely done. So -3/10 I is equal to yi.
Divide the i's.
Divide the I out. We get y is equal to,
3.
so we're done. Okay? Let's get Colton a hand.
Good job.
Question.
For this one,
This
If-
is not bad.
if that's the negative, you brought the I over here.
Yeah, so in this problem, and I apologize for not including the negative before, but I can take a negative I and divide it to the other side because I want to get y by itself.
Just number.
Yeah, and you can cross out the negatives. Because remember, anything divided by itself is gone.
But you put the negative over there.
Man, it's spicy.
Yeah, I should have put there as well.
Smashing my knuckles.
There's just laziness on my part, but when you're dividing the negatives, you gotta take the negative with you to the other side. Which will make that. The i's cross out too. We got I divided by I, we got I divided by I.
About that. I better
Keep
back
track of
it
those
up.
i's.
Actually, give it
Okay,
back.
same thing over here.
No, do
We
it.
took my I over.
Do it.
There was already an I already waiting over here, so we could cross both of these out, because in both cases we were dividing I by itself.
You can do it. That's what I'm gonna give it back to you.
How you dealing with this imaginary stuff so far?
It's the math isn't hard. It's just understanding the steps.
Okay, the math isn't hard, the steps just are a little tricky.
Yeah.
Is that a first statement? Okay. Let's do something even trickier. Let's say we give you something that looks like a factoring problem and have you solve for x.
Oh, I hate those.
Isabel, we're recording a lesson. We don't want our viewers to have negative vibes. Alright?
Yeah.
Positive thoughts.
I love these. Just edit it out.
Isabel, what is that? What is that? What is that? You better kill that. Portland, they'll tell you that. I think it's just about him.
Okay.
Kill it. No, it's
All right.
Kill it.
Next. Next topic. Can I erase that as well?
Yes.
I'll just get rid of it.
Not the red part.
Can I erase the purple at least? Next topic. Finding zeros of complex quadratic functions. Okay? For example, let's say we have the equation f of x is equal to x squared plus 10x plus 26. Okay? I hope I've trained you guys well enough so that whenever you see a standard form of a quadratic, you start to factor. Always factor when you see a trinomial. So can we find two numbers that times to be 26 and add to be 10? I can erase it? Okay. Are there two numbers that times to be 26 and add to be 10?
Nope.
Saying no? Does anyone agree that there's nothing that works?
It would have to be a decimal or a fraction.
Yeah, it's nothing at least nice, right? So what do we do when we can't factor?
Find the perfect square.
We complete the square, right? So what we learned yesterday. So I'm going to give up factoring since I can't do it. What was my first step for completing the square?
Subtract 26 over.
Okay, we got to get my constant isolated and my variable terms isolated. And remember, the whole process of this, the whole goal is to find zeros. So I'm going to set this thing equal to 0 first. And then just like Noah says, we want our constant on the other side of the equal sign as our variable terms. So we'll subtract that. So we have negative 26 is equal to x squared plus 10x. What was our next step of completing the square?
Get the b.
Yeah,
B over 2.
Yeah, we got to add b over 2 squared to both sides.
10.
So 10 is our b. So if I'm adding 10 over 2 squared to both sides, what's 10 over 2 squared?
25.
Yeah, 10 divided by 2 is 5. 5 squared is 25. So if I add 25 to both sides, let me change colors really quickly. Add 25 to both sides. Now we have something we can simplify. 25 plus negative 26. What is that?
1.
Negative 1. Good. So negative 1 is equal to x squared plus 10x plus 25. What's our next step for completing the square?
You subtract 25.
Not yet, not yet.
You can factor it.
We can factor it.
Oh,
How do we factor this guy?
You find out what multiplies to be c and adds to be b, which is 5.
Okay, so 5 times 5 gives you 25. 5 plus 5 gives you 10.
That's x plus 5.
So x plus 5 squared. I could have written another one next to it, but just keep in mind we're timesing it by itself. So I'm kind of skipping that step. And how am I going to get x by itself now?
Get the square root.
Okay, so we square root both sides. Uh-oh, we're rooting in negative. So that's why this is complex. Okay, let's move over here just so people can see. So we've got negative 1 rooted. Let's go up here. Negative 1 rooted is equal to x plus 5. Okay, how do I get x by itself?
Subtract 5.
I have a question.
Question?
Do you have to put x or positive or negative before?
Yes, I forgot about that. Thank you.
Because, okay. What would be next? We get to subtract 5.
Subtract 5 from both sides. Okay, so x is equal to positive or negative root negative 1 minus 5. Am I done?
Don't you like multiply the negative 1 times negative 5?
Well, we don't multiply because we're simply subtracting. Okay.
Okay, so you'd make it negative 6.
We can't do that because this is not a whole number. This is an imaginary number.
That's it.
Alright.
Well, it's good. But what did we say that root of negative 1 was?
Imaginary, you can simplify.
I.
I.
So we could put our I in there. So we could say x is equal to positive or negative I minus 5. Okay? Good. Make sense?
Wait, why'd you take away the -1?
Then it equals I.
Because this is our imaginary unit. We defined I as the root of negative 1. Okay?
Okay.
Cool. And let's check our answer. Were we right?
Yeah, we're right.
They kind of flipped it around. They said -5 plus or minus I,
It's fine.
but same thing. Same thing. Good. We might almost be done. One more topic for the day, and then we're done. How far can I erase?
Just erase all of it.
No. Like,
What?
need that side.
He needs the right side.
Yeah.
Okay, but I can do the left. Okay. Okay, so next topic. Let's talk about complex conjugates. Complex conjugates. Okay? Okay. Question.
One question. It's just, does it always have to be -1 or just any negative number equals I?
Well, only root -1 is I. But remember that if you have any other number that's negative, like 16, like we saw with Isabel, I think, she broke it up to be -1 times 16, which she could then bring out to be 4 -1, which would then be 4i.
What if the number?
So I itself is only root of -1.
What if you can't square root the number?
You can't square root it. Like, let's say,
It's
it's a
like
good question.
-1 and not -3.
Let's say, let me give you another one that's kind of a little bit more complex than that. Let's say we're doing the root of -27. Okay? If we're doing the root of -27, can I break this number up into a perfect square factor?
No.
Is there a perfect square that goes into 27?
3-7. No, not 3-7. What am I thinking?
Is there a perfect square that goes into
9-7.
9 and 7, right? Stop giggling, guys. Gosh. We could rewrite -27 as the product of, let's say, 9 and -3.
Oh yeah, 9.
We could bring out 9's root. I forgot my plus or minus. So it's 3 root -3. Okay? But because we've got a negative number, we could break up that -3 to be positive or -3 times the root of 3 times -1. Okay?
Okay.
We know the root of -1 is what?
I.
I, right? So I could say positive or -3 root 3, and I could times that all by I. Okay?
Why would you move I outside?
Just
Yeah.
because it's convention for us to put i's at the end of any constants, but because the 3 is still being rooted, we're gonna put that at the very end. I could have just as easily have moved the I over here or in front, but it doesn't matter the order in which you multiply things. 3 times I times root 3 is the same thing as 3 times root 3 times I. So yeah, that's a great question. So you can still have roots, but just make sure you bring that negative out as an I. Okay? Does that feel good?
Yeah.
Sweet. Brennan, did you finish?
Yeah, I got it.
Okay. I'll get the brown out of the way.
It's a happy parabola.
Oh, my camera's still going. Good it is. Okay, so complex conjugates. Take a look at these two complex numbers. Let's say we've got -5 plus root of 10. Actually, hold on. I read the den wrong. Let's say we have -5 plus I root 10. And let's say we have -5 minus I root 10. What is the difference between these two things right here?
It's just a negative.
One's got a plus,
So it's a-
one's got a minus. Okay? A conjugate basically means you've got the same thing, you're just switching the operation. Okay? Let me write that down. Okay, so a conjugate. A conjugate,
You want a definition?
a conjugate of a complex number is the same.
Wait, so those are two different equations?
They're two different things, but they are conjugates because the only thing that changed was the operation. So a conjugate of a complex number is the same, but with an opposite operation. Okay? So negative 5 plus I root 10, negative 5 minus I root 10. Those are conjugates. Okay? Cool. All right. Let's talk about why this is useful. Take a look here at example A on the screen. If I gave you 8 plus 5i and asked you to find the conjugate, can someone walk me through how I would find the conjugate?
If you just start 8 minus 5.
8 minus 5i, right? So all we're going to do is take the exact same thing, but just switch the operation. So the conjugate is 8 minus 5i. That's probably the easiest thing we've done all day, right?
False.
False.
Writing my name on the paper.
You're funny. Okay, let's say I gave you something that looks like this. It's just plain old 6i. How can I find the conjugate of plain old 6i?
Negative 6i.
How'd you do that?
It's just the opposite.
It's the opposite, right? So if you're looking for something that looks like this, and you just got plain old 6i, you could make your own real number and just say, okay, what if it's 0 plus 6i? The conjugate would then be 0 minus 6i.
Okay.
Okay? Yeah.
How come if it's the opposite, the sign wouldn't change?
What do you mean?
Like, it's negative 5, but it doesn't become a positive 5. Up there.
Oh, here?
Yeah.
Only the sign in front of the imaginary unit changes. And
Nothing.
here's why. Remember how the root of anything has both a positive and a negative solution? That's why. Okay? But the real part, that sign doesn't change. It's just the operation in front of the root that changes.
What operation?
The operation that's in front of the imaginary unit.
Oh, just don't change the negative.
And the reason why, okay, so let's write this down. With a little star next to it.
That's tricky.
The reason for switching the signs is because all roots have a positive solution and a negative solution. That's why we switch the sign. That makes sense? Okay. And we're done. Okay? Question?
Could you do that with multiplication? and
Mr. Mayor,
division?
should upload these lessons online.
Like switching signs?
Oh wait, never mind, because it wouldn't be.
Conjugates is only with addition and subtraction.
Mr. Mayor.
Any other questions?
Nope.
Sweet. Let me shut my camera off.